স্যার মানে within a sphere electric field strength zero কেন মানে I guess you answered it but ভুলে গেছি
Charges have a inherent property to always remain on the surface of the object. To always remain on the surface of the object. And from the surface, the electric field lines go outwards, not inward. That's why inside the sphere, I mean, if you penetrate to the surface of a sphere and go inside, you'll find no electric field there because the field lines are always going outwards because charges are trying to repel each other. See, like charges are trying to repel each other.
Oh yes sir, I got it. Thank you sir.
Sure. Okay. Asadul Amin, give me a problem. I'm gonna put it into the all chat. তোমার যে প্রবলেম দিয়েছো অল চ্যাটে লেখো তাহলে সবাই একটু বুঝতে পারবে যে কোন প্রবলেমটা আমরা আলাপ করতেছি। ধরো আমি এটা কপি করতে পারবো না। হ্যাঁ হ্যাঁ না আমি এটা কপি করতে পারতেছি না। আচ্ছা Asadul Amin gave me a problem from the electromagnetism worksheet, so which I'm gonna go to electromagnetism worksheet হচ্ছে booklet 2 না 3 হ্যাঁ 2
স্যার
বলো
স্যার আমাদের ফুল মক রুটিন কবে দেওয়া হবে?
তোমাদের মক রুটিন আর এক উইকের মধ্যে দেওয়া হবে কারণ তোমাদের টপিক টেস্ট হবে হচ্ছে জানুয়ারি মাসে আর ফুল সিলেবাস মক হবে হচ্ছে ফেব্রুয়ারি মার্চ এপ্রিলে, সো ইউ উইল হ্যাভ ইট।
মানে রুটিন স্যার নেক্সট মান্থে পাবো?
এই এক উইকের মধ্যে পাবা রুটিনের কাজ করতে।
ওকে স্যার।
ওকে ইলেকট্রোম্যাগনেটিজম ওয়ার্কশিট কোশ্চেন নাম্বার 1A, এই ড্রয়িংটা তো ওই দিনও দেখাইলাম,
অনেক আগেই দেখাইছেন স্যার এটা।
আচ্ছা সমস্যা নাই। Asadul Amin gave me a problem, so I'll explain this, no big deal. বুঝাচ্ছি আমি, don't worry. তারপর হচ্ছে BI,
স্যার আমাদের মক অ্যাপ্রক্সিমেটলি কবে শুরু হবে?
তোমাদের জানুয়ারি মাসে পুরোটা হবে হচ্ছে তোমার টপিক বেস মক, আর হচ্ছে ফেব্রুয়ারি মার্চ এপ্রিল হবে ফুল সিলেবাস মক।
আচ্ছা স্যার।
Additional problem, তোমার প্রবলেম দেওয়া শুরু করো, write other problems so that we can actually take these on whenever I'm done with here. So the first problem that we have is this question. Let me lower this place. আচ্ছা এখানে এটা সলভ করার বেসিক আইডিয়াটা হচ্ছে there are few things that you need to understand. জিনিসটা খেয়াল করো, whenever we have a transformer or we have the case for electromagnetic induction, the primary coil current, the magnetic flux produced in the primary coil, the magnetic flux linkage of the primary coil, they are all produced in the same phase. So the graph of these three versus time will always have the same shape: primary coil current, primary coil magnetic field, and primary coil flux. Whereas the EMF generated in the secondary coil, so EMF in the secondary coil is given by minus d phi by dt. এই ফাইটা হচ্ছে প্রাইমারি কয়েলের প্রডিউসড ফাই, বিকজ এই ম্যাগনেটিক ফ্লাক্সটা ইভেন্চুয়ালি আমাদের সেকেন্ডারি কয়েলে এসে আমাদের ইএমএফটা ইনডিউস করবে। সো দ্যাটস ওয়াই, এন্ড দেয়ার ইজ আ মাইনাস ওভার হিয়ার। সো ফার্স্ট অফ অল, হোয়াট এভার দ্য গ্রাফ অফ the primary coil versus time is, we have to first differentiate that graph. So we have to find out the gradient of that graph and plot the negative of that gradient onto the EMF graph. এই লজিকটুকু বুঝছো কিনা দেখো আগে। Asadul Amin,
আরেকবার রিপিট করবেন?
Sure. Whatever the graph you have over here, for example, you have over here that let's say phi, এখানে আমাদের current versus time graph দেওয়া। So this is the current of coil A. So this is the primary coil current. So primary coil কারেন্টের যে গ্রাফটা হবে, আমাদের সেকেন্ডারি coil ইনডিউসড ইএমএফ এর গ্রাফের জন্য আমাদেরকে এই শেপটা জাজ করতে হবে, because these three things will always have the same shape. এবং এই গ্রাফের ডিফারেন্সিয়েটেড ভ্যালু মানে হচ্ছে গ্রেডিয়েন্ট। সো এই গ্রাফের যে গ্রেডিয়েন্ট হবে সেই গ্রেডিয়েন্টের নেগেটিভ যে ভার্সন, মানে জাস্ট পজিটিভ নেগেটিভ ফ্লিপড। সো এই গ্রাফগুলোর নেগেটিভ গ্রেডিয়েন্ট আমাদেরকে প্লট করতে হবে হচ্ছে ইএমএফ এর গ্রাফে, বিকজ অফ দিস ফর্মুলা।
Okay, sir.
ঠিক আছে? So the way it works is that if you have a look over here, let me bring this to a bit closer so that it's easier for us to see. So এখানে যদি খেয়াল করো যে আমাদের ফার্স্ট, হ্যাঁ বলো
স্যার, আপনি যে প্রথম যে ইকুয়েশনটা দেখালেন ওটা স্যার ওইটা বেসিক্যালি কোন ইকুয়েশন থেকে আসতেছে?
Faraday's law of automatic induction.
ও আচ্ছা, বুঝতে পারছি।
আচ্ছা, so এখানে আমরা যে জিনিসটা দেখবো, so let's just try to observe the gradients of this whole graph part by part. So first part এ দেখো এটা হচ্ছে horizontal line এর gradient 0, তার মানে হচ্ছে আমাদের ফার্স্ট পার্টটাতে আমাদের ইনডিউসড ইএমএফ হবে হচ্ছে 0, so we're gonna draw a perfectly horizontal line over here. এই পার্টটুকুতে আমাদের গ্রেডিয়েন্ট হচ্ছে 0, সো আমি কনফিডেন্টলি এই পার্টটুকুতে 0 রেখে ফেললাম। আমি এই দুটো পার্ট আগে আঁকতেছি বিকজ আমি দেখতেছি যে এই দুটো পার্টের গ্রেডিয়েন্ট 0, সো এই দুটো পার্টে কোনো ইএমএফ ইনডিউস হবে না কারণ কারেন্টের ভ্যালু কনস্ট্যান্ট। Then go for the changes. If you have a look for this part of the graph, have a look, this is a curve, and the way you can see that if you try to visualize the tangents of this curve in different places from left to right, you should be seeing that you have the gradient of the curve slowly decreasing. এখানে হচ্ছে স্টিপার গ্রেডিয়েন্ট, এখানে হচ্ছে লেস গ্রেডিয়েন্ট। তার মানে হচ্ছে এখানে আমাদের গ্রেডিয়েন্টের ভ্যালু বেশি, এখানে গ্রেডিয়েন্টের ভ্যালু কম, and all of these tangent lines represent positive gradient. Because the gradient is positive, so the EMF generated over here should be negative because of the minus d phi by dt minus EMF equals to minus d phi by dt. Because these are all positive gradients, here we'll have negative values. At the start point we'll have high negative values because these are more bigger gradients, and as you slowly go from here to the right of the curve, you are actually losing gradient. So you suddenly from this 0 EMF we should have a pretty large negative EMF coming from the positive gradient reverse version, and then it should slowly drop to 0. Now this dropping to 0 can be shown to be a straight line, so there should be definitely a continuation line right over here. So this dropping can be shown to be with a straight line, or you can show it to be a negative gradient, you can show it to be a positive gradient. Any of these three shapes are acceptable because in this case we can only see that the EMF is decreasing. We do not know how the EMF is decreasing. The EMF might be decreasing linearly, the EMF might be decreasing in a negative gradient, the EMF might be decreasing in a increasing gradient. So we cannot essentially say from the shape of this I versus T graph that how this decrease will happen. So you could draw any of these three shapes either. You don't draw all three. Typically students go for the straight line. Straight line is the most common choice because it's easier to remember, but logically speaking this could be any of these three. The EMF will, from a high negative value, the EMF will slowly become 0. That's the part. এই পার্টটা বুঝছো কিনা আসদুল আমিন?
জি স্যার।
আচ্ছা, বিউটিফুল। তো তারপর হচ্ছে এই পার্টটুকু গ্রেডিয়েন্ট হচ্ছে 0, সো এই পার্টটুকু গ্রেডিয়েন্ট 0 হলে তাহলে এই পার্টটুকু তো পারফেক্টলি 0 হবে, হরিজন্টাল লাইন। And then you can see over here we have a very steep negative gradient straight line. This is a straight line. Straight line মানে হচ্ছে constant gradient. এটা কিন্তু this was a curve, which means this was a very varied EMF. This is a straight line of negative gradient. Negative gradient এর জন্য, for the negative gradient we will have a positive EMF, so which means this EMF should be a pretty high point over here, but that EMF should be a constant value because this is a straight line. Straight lines have constant gradient, so suddenly there should be a rectangular spike. So use rulers to draw more better lines. I'm not using rulers. So this is this part, and then you have to continue this graph all the way up to the end point of this arrow because this
লাস্টে ওরকম হলো কেন?
value is actually shown all the way to the right. So continue this graph all the way up to the last point. You just overlap onto this drawn line, and that's basically it. হ্যাঁ, শুভ কি বলছো?
স্যার থার্ড স্টেজের ব্যাপারটা বুঝলাম না স্যার।
This is a graph with negative gradient, but constant negative gradient. This is a straight line. So you have a constant positive voltage. So the voltage should be, for this duration, the voltage should be flat, but it should have a constant value for this small duration. So there should be a sudden rise, constant, and then sudden fall, and then back again to 0.
জি স্যার।
So আসলে আমি বুঝছো এই পার্টটা বুঝা গেছে?
জি স্যার।
আচ্ছা, This is actually a more of a theoretical graph. Theoretical graph because what I'm saying is that you can see over here that the changes of the primary coil is actually affecting the secondary coil EMF generation instantaneously. That's what we're showing over here. But for a practical transformer, we have some things called resistance. We have some things called inductances. Together they make an impedance factor for the coil scenario. And as a result, typically the secondary transformer has a little bit of lag. The secondary coil has a little bit of lag compared to the primary coil to show these changes. So there is always a little bit of lag between these two phases. This can be overcome by using some appropriate capacitor thingies. I'm not sure how this can be overcome, but in practical cases, there is always some lag. This is drawn for an ideal transformer. Ideal transformer means that we do not have any of the problems over here. These coils are considered to be perfect conductor coils. We are considering none of these electromagnetic fields are getting stray. So let's say all the electromagnetic fields are getting over here. And because we do not essentially have any value scales on the y-axis, so we don't have to bother about the magnitudes. I mean, no matter how long or how small or big you draw, you're perfectly good because you don't have to do calculation. All that you have to understand is the phase difference. So that's the phase difference information. We use the term phase difference because this is differentiated graph, and also there is a minus, which means this is reversely phased. So that's how we deal with this graph. Among all the problems that we've given over here, I'm gonna go for the other question that relates.
Sir,
to
magnetic
graph.
flux magnetic flux versus time graph যদি দিত স্যার
Primary coiler na secondary coiler?
স্যার প্রাইমারি কোয়েলেরই
It would be the same shape.
মানে কারেন্টের সাথে তাহলে তো সেমই হবে
Same shape হইতো। With just to time, it would have the same shape. Yes. This is one of the other questions that you have given in the list. So this is actually easier for me to discuss because it has the same principle. That's why I'm picking this up right now. Never mind. Let's just make this a bit bigger. Take it over here. Zoom out. So zoom. So এখানে দেখো হচ্ছে এখানে আমাদের basically তিনটা গ্রাফ আঁকতে বলছে, and it's pretty much the same concept. First, we are given the primary coil current versus time, and here the phi is for the primary coil as well. So if we have a look at the question, just to give you a better idea, the question says that an ideal iron core transformer is in illustrating figure 6.1. We have the input coil, we have the output coil. So input coil has fewer core turns, output coil has fewer turns, which means this is a step-up transformer. Voltage should be increased and current will be decreased. So it just there are some questions over here. এটা তো problem নাই, এটা problem আছে? No, it's not. Here be the graph to the problem. So I'll help you for the graph. So in this case, we want to show the terminal, there is no current in the coil. Complete figure wants you to show the variation temperature of the magnetic flux in the core. So the core will hold the magnetic flux that is produced by the primary coil, which will then cut across the secondary coil and produce the EMF across the secondary coil, which means similarly, this phi is basically the magnetic flux produced by the primary coil, because the primary coil produces the flux, which in turn produces the EMF in the secondary coil. So these two graphs should have the exact same shape. Like I said, that primary coil current, primary coil magnetic field, primary coil magnetic flux, they all have the same shape with respect to time. However, this is the EMF graph, which means this should be minus d phi by dt of this graph. So if I just take out, we have already taken out this image. So have a look. This will be actually a sine curve. So drawing this graph would be actually pretty simple. I can actually take a bit of a shortcut because I'm in a computer environment. So why not? Let me just steal away this part and copy paste it over here. And that's basically it. So this is how the phi versus t graph would look like. Exactly same shape, no difference. However, the EMF versus t graph would be something different. Have a look. This is a sine curve. This is a sine curve. So তুমি যদি এটাকে d by dt of sine t minus করো, what shape are you gonna get? Sine curve কে ডিফারেন্সিয়েট করলে হবে হচ্ছে cos curve,
স্যার
cos curve versus sir.
এবং তার সাথে একটা মাইনাসও থাকবে, সামনে একটা মাইনাসও আসবে, ঠিক আছে? তারপর আমাদেরকে নেগেটিভ cos curve রাখতে হবে। নেগেটিভ cos curve মানে কি রকম? It should start from -1 and then you should just continue. So which means once again I can copy the whole thing and try to help my drawing process. Let's say I'm gonna copy up conveniently the up to this point. So what I'm trying to draw is from here, A2, and then maybe I'll, no, steal this part, okay, and then rub out the remaining. বুঝা যাচ্ছে কি করছি? I'm just skipping the process of drawing it by my hand because it's very difficult to draw in the on the drawing board. So that's how the graph will look like, because this is a sine curve. So if you revert this to cos curve, and then if you put the minus, it becomes a minus cos curve. So that's basically the shape. বুঝা গেছে কি?
Yes, sir.
Beautiful. So the other problem that you gave in the list was from this question. From this question, that figure 6.4 is a circuit for a bridge rectifier and alternating power supply connects across PR has an output of 6 volt RMS. So this is 6 volt RMS supply. On figure 6.4 cycle, those diodes that are conducting with when R is positive with respect to P. So what does this mean? So let's say we have to label a circle. The circle will say naki. Yeah, circle those diodes that are conducting when R is positive with respect to P, which means R is positive with respect to P. তার মানে হচ্ছে এখানে কারেন্ট এখান থেকে এদিকে আসবে। So এই মার্কগুলো আমি দিয়েছি হচ্ছে আমার সুবিধার জন্য. You can also mark on your figure because that's what the question said, but you are not going to be scoring any marks for this labeling because that's not necessary. So try to think about it. Current is entering this diode, full bridge rectifier diode structure from the R point. Once it reaches over here, try to understand the current cannot go through this way because this is the reverse bias. Current can only come in here. After it comes over here, the current cannot go to the P. It want to go to the P because this is a low voltage point, but it cannot go to that point because of the diode orientation. So the only way that the current can travel is go to right, and eventually it should enter the load through down. So in this case, this diode would be carrying the current. So current comes in, goes to the R, then falls down to the load, goes all the way up over here and reaches to S. এই পর্যন্ত বুঝছো কিনা যে কেন ডায়োড কারেন্ট এই দুটো পাশ দিয়ে পাস করবে না? Why the current would not go through this diode? এটা বুঝা গেছে?
Yes, sir.
Yes.
So it passes through here, goes through the load, goes all the way up to the S point. This is the junction point. Now once it comes to the S point, it practically has both of the diodes in forward bias. The current logically can go through here, the current can logically go through here. But if you always understand the current, to complete the circuit, the current will always have to go from high voltage to low voltage. So current actually was entering through this path. If the current goes back over here, it will try to oppose to this path. It will never go in this way. The current will essentially go to the negative voltage supply so that it can complete the whole circuit. So in this scenario, the pathway of the current is going to be like something like this. Let me just draw this with red to make a better sense with you. So it flows through here, which is up here, and then it doesn't go down. It goes up, and eventually it flows all the way back to the supply. So that's how the current flows for this half cycle when R is positive and P is negative. So in this case, two of the diodes which are working, one is this one and the other one is this one. For the next half cycle, the opposite two will be working. For example, if P was positive and R was negative, then the current will be flowing through the other pathway. But in the load, the current will always go from top to down. So, or for the load, this will always be the positive end, this will always be the negative end. So that's how the rectification is done. বুঝছো?
Yes, sir.
পরের পার্টটা কি বুঝছো? আমি পরে যেটুকু বললাম নাকি ওটুকু এঁকে দেখাবো, এঁকে দেখাতে পারি?
না স্যার লাগবে না।
আচ্ছা, আচ্ছা, এরপরে আরেকটা যে প্রবলেম তুমি বলছো এখানে, সেটা হচ্ছে ম্যাডিফিল্ডের এই কোশ্চেনটা নাম্বার 4. আচ্ছা, নাম্বার 4 এর কোশ্চেন আমরা দেখি। Two long straight current carrying conductors PQ and XY are held in constant distance apart as shown in figure 6.1. বলুন, 1 মিনিট আমি একটু আসতেছি।
Sir, I can't hear you.
Oh, sorry. Sorry. I mean, unmute করতে ভুলে গেছিলাম। হ্যাঁ। Did I just unmute myself? I think so. আচ্ছা হ্যাঁ, বলতেছি আমি কি করব। So let's try to understand the question part by part, because this can be confusing because both of these wires would be actually exerting force onto each other. We don't want to have perplexing figures. We want to draw precisely what the question is asking us to draw. So you have to understand the question very precisely. Have a look. On figure 6.2, draw arrows, one in each case, to show the direction of magnetic field at Q due to the current in wire XY. So magnetic field that is produced by current XY at the location of Q. Now this is the XY wire, the current is coming out. So if you use the right hand grip tool, the magnetic field produced by the wire XY would be anti-clockwise arrow like this. You can have concentric arrow circles bigger and bigger and bigger, which means essentially, because this Q point is pretty much on the left, the magnetic field direction would be vertically downwards. So I'm going to draw a vertically downwards arrow over here and label this arrow as B. See if it makes sense. This arrow is actually a small arc, or you might also say a tangent of a large circle. If I draw a very large circle, let's say I'm gonna rub off this circle after a while. Let's say I'm gonna draw this much of a big circle, like this much. So something like this. So if it's a big magnetic field line that passes through the point B, this arrow that I'm drawing is basically the tangent of that circle at that point. So that's representing the instantaneous, this showing the instantaneous the localized, localized is the correct word, that will show you the localized direction of that magnetic field at that position Q. এটা বুঝে গেছে কিনা?
এটা একটু আরেকবার বুঝান।
আচ্ছা, কোশ্চেনটা বুঝো আগে। কোশ্চেনে বলছে হচ্ছে on figure 6.2 draw two arrows. So first we're going to try to solve B1. It says draw the arrow at Q due to the current in wire XY. And XY এর জন্য যে কারেন্টটা যে ম্যাগনেটিক ফিল্ডটা হবে, সেই ম্যাগনেটিক ফিল্ডটা অ্যাকচুয়ালি কি রকম হবে? আচ্ছা, ম্যাগনেটিক ফিল্ডটা আমি আগে এঁকে দেখাই, কারণ if you can visualize this, it would be very difficult for you to understand. আমি দেখাচ্ছি, hold up, I'll show you in a better way. Can we have perfect circle view, top view, top view, top view? These are good pictures, except for, can I use this? How big are these? No, they're not so big. This is well workable. Okay, let me choose this one. Copy image, paste it here. Select transparent selection. Okay, transparent selection. This much. Okay, transparent selection is not helping. Can I color picker white and then make everything white? Should this help? I hope it does. Beautiful. So this is how this is gonna look like. For the dot wire, if I place them overlapping over here, this is the magnetic field shape that's gonna produce. And this is not the limited field. As we slowly go further away, the field would be the field can theoretically go infinitely big, and there'll be concentric circles. So just to make sure that how this would look like if this figure comes up over here, let me just expand this thing and show you a more expanded view for how it's gonna look like. For example, if I now place the circle over here, center over here, you're gonna have downward field at the Q position because of the wire XY. Does it make sense now? So that arrow that I was trying to draw was basically the direction of this whole magnetic field exactly at location Q. That was the arrow that I was trying to draw. বুঝে গেছে?
জি স্যার।
Beautiful.
ও তো স্যার, তাহলে ওই এক্সাক্ট পয়েন্টে আর্ক ড্র করলে ভুল হবে?
Well, you will draw a very small handheld arrow. I mean, if you want to draw an arc with using this as a center of a compass, I wouldn't recommend this because drawing an arc would represent the magnetic field of that much location. The question doesn't ask us to draw the magnetic field for a certain space of location. It specifically asks us on at the point at Q. At Q means at a specific location. Now, if you think for a circle, I mean, if you consider a circle, a certain segment of a circle can be considered to be arc. But if you consider a certain point of the circle, what is the direction exactly at this point? That would be represented by the tangent on that circle, right? So drawing an arc in this case, in my opinion, would be a wrong thing. You need to draw a perfectly vertical arrow using a ruler downwards.
Got it. Thank you.
Beautiful. So that's the first thing. And then the second question, the second part, it says that the force at Q as a result of the magnetic field due to the current in wire XY label is arrow F. So force at Q. So how this Q wire would be experiencing force because of the wire XY. This is something from your O levels that if you have parallel wires carrying current in the same direction, they actually attract each other. So because the magnetic field, let me just show you the magnetic field line orientation. Magnetic field. So exactly, this is the figure that I was looking for. Or maybe this one also helps. Yeah, either way. This is actually a more detailed view. If you consider the individual field lines for both of the wires, this is the scenario that we are now working with. We have dots and dots. So the magnetic field lines are actually are in opposite direction for the in-between space. Have a look that this wire is producing upward magnetic field lines along to the right side. This wire is producing downward magnetic field on the left wire. So which means for the in-between space, they'll be producing opposite magnetic field. Because of the opposite magnetic field, they will become weaker. And as a result, we'll be having a scenario like this. So in the in-between space, the field lines will be really, really weak. But on the outsides, the field lines will be pretty strong. And field lines always repel each other. So the outer field lines are going to try to compress the inner field lines, which will essentially put pressure onto the two wires to get closer to each other. That's basically how we define the attraction. And vice versa for opposite field lines. For the opposite direction of the current carrying pair, we have similar direction of magnetic field lines over here, which basically tries to push them apart. So that's what we define as repulsion between the two pieces of wires. So in this case, there will be just attraction, which means for this case, wire Q will be experiencing a force to the right, and wire Y, XY, will be experiencing a force to the left. Because we are exclusively asked to draw the arrow on the wire Q, have you read the question? The force at Q as a result of the magnetic field due to the current XY. So what is the force working at Q because of the magnetic field of the Y? So that would be towards Y. So that's why we have to simply draw an arrow from this dot. Oops, sorry, wrong color. So we have to draw a horizontal arrow and label this F. So please do use ruler to make this line as vertical as you can. You don't have to essentially use a protector, and then you draw this line to be horizontal. Preferably hold up your ruler against both of these dots and draw a small arrow and label this arrow as F, and that's pretty much it. বুঝে গেছে?
Yes, sir.
Beautiful. The next problem that you have proposed was number 5.
Sir.
Yeah, Abias bolo.
Magnetic field lines have a tendency to be either perfectly circular or perfectly straight.
I don't know nothing about that. Magnetic field lines repel each other. That's what I know. Magnetic field lines don't have a natural tendency to take any shape. They are directed by the presence of the magnetic sources, magnetic field sources within the space.
So they tend to repel each other when they're too close together.
Yeah. Even if they're not close together, they'll repel each other because the extension of magnetic field and electric field can be virtually infinitely big. So you have magnetic field lines, they will repel each other, period. The closer
Okay.
there, the stronger is the repulsion, or the stronger is the repulsion. That's the important thing. That's why obviously you should understand that whenever we have this thing close to the wires, the magnetic field is really strong because the field lines are really close to each other. The farther you get, the field becomes weaker.
Okay, sir, I understand.
Beautiful. So the next question will be number 5. The number 5B is actually here. The first question is actually pretty simple. It says that an ideal transformer has 5,000 turns on its primary coil. It is to be used to convert a main supply of 230 volt RMS to an alternating voltage having a peak value of 9 volt. Now this is the important bit. The primary voltage coil is given for an RMS value, and the output has to be a peak value of 9 volts. So they are not the same type. This is an RMS value, this is a peak value. So you cannot essentially do the calculation having these two values placed in the same equation. Either you have to convert the RMS into peak and do your calculation using peak and peak, or you have to convert this peak into a relevant RMS value and do your calculation using RMS and RMS. You cannot use both of these values within the same equation because they are not the same type of voltage. One is the peak voltage, the other one is the RMS voltage. So doing this part is actually pretty simple. I'll try to take it out. Actually, I am missing the question here. I'll take the question, just a second. So here it says that so we're trying to we have a transformer coil over here. So what we know is that for any coil, for any transformer, voltage primary divided by voltage secondary is given by number of turns in primary divided by number of turns in secondary. So like I said, that we either have to do one thing. So I'm not essentially doing a second step for doing this thing. I'm gonna only convert this thing into peak voltage because the primary coil is 230 volt RMS, means the peak would be 230 root 2. This will be the peak value. You just multiply it by root 2, you get the peak value. And here I'm gonna just place the peak value. So now both of these voltages are peak value voltages. So this is also peak supply voltage. This is also peak output voltage. And the primary coil turn was 5,000, and you want to find out the secondary coil turn. So you just get this number, and that's basically your answer. But you cannot do 230 by 9.0. That would be wrong because they would not be of the same type. This is the first question, and the number B says, and the output from a transformer is to be full wave rectified. Figure 4.1 shows the part of rectifier circuit. On figure 4.1, draw diode symbols to complete the diagram of the rectifier, such as the terminal A of the resistor R is positive with respect to terminal B. The symbol for the capacitor connected to the provides smoothing to the potential difference across resistor R. Acha. So, okay, what we want to achieve is this. Can show history. Who wanted history? The question is this and this. Okay, they are all individual. No problem. কি করলাম? Okay. So in this question, it first says that the output from the transformer is fully rectified. Complete figure 4.1 showing diode symbols to complete the diagram of the rectifier such that terminal A of the resistor R is positive with respect to terminal B. So what we want in this case, terminal A has to be positive and terminal B has to be negative, which means current through this R should go down. First thing that you need to understand this. So if current has to go down, current has to flow outwards from here and current has to flow inwards from here. So there are many different ways we can actually approach this thing. There is a way of basically remembering how the circuit works. I'm going to tell you that first, and then I'm going to logically show you that this is actually correct, because you cannot judge the circuit unless you draw it. So you have to draw it by pencil. Then you can proof check it, that did I draw it correctly, and if it's wrong, then you can erase and redraw it. The easier way to remember that how the diodes are always oriented is just to have a look at this circuit that we just solved a little bit earlier. Here you can see. Have a look at this structure. The full bridge rectifier, structure is always such that the two diodes on the parallel sides or the opposite sides of this kite structure is that they are always in the same direction, and the point of the load which is supposed to be positive, that's where two of the diodes are always aiming to. You can see that this diode is aiming to the positive head. For this figure, this was also the positive end, and this diode is always also aiming to the positive head. So these two diodes will, the aiming diodes, the two of the diodes will be always aiming towards the positive end, and the opposite sides are always going to be in parallel direction, which means these two are in the same direction, these two are in the same direction as well. So this is an easier way to remember. So if I just use that to draw this part, so here I want this one to be my positive output, and this one to be my negative. So if this is supposed to be my positive output, so my diode for this part, two of these diodes should be aiming here. And then you use the idea of parallel. So if this diode is going this way, this diode should also go this way. If this diode is going upwards, so this diode goes upwards. Now you can proof check this circuit for the sake of being confirmed. So the one way is that if we consider that, let's say for the transformer, this is a symbol for a transformer, or is it an inductor? I think this is a transformer. If this is a positive and this is a negative end, because this will alternately change. So the current in this case will go through, have a look over here. Current comes here, cannot go right, it will come here, flow through here, go all the way up here, going through the resistor, coming back to this point, which is up over here. Now the question is it going to go up or down? Now have a look. The up was a positive voltage, it's not going to go up. It's going to come to a negative voltage and flow like this. So in this case, A is positive, which is good. What if we consider the reverse version? If A is, this side is negative and this side is positive. So this the current starts from here. Let's have a look. Current starts from here. Cannot go to the right because the reverse bias of the diode goes up, which is over here, and cannot go through the diode combination because that's the reverse bias. So it goes through the pathway, flows through the resistor, reaches up over here. And once it reaches up over here, it will not go down because this is the positive high voltage. This is the low voltage connection, and eventually flow back to the transformer. So basically your circuit is perfectly done. So if you remember this part, that the positive end is basically where two closed diodes are always aiming towards resistance. So if they are aiming this way, this will be a positive terminal point. So that's easier to remember. Epata bucho.
Yes, sir.
Beautiful. And then they also say that
স্যার আমরা তো
হ্যাঁ
স্যার
বলো।
আমরা তো রেজিস্টরের মানে অপোজিট সাইড থেকে হচ্ছে প্লাস ধরতে পারতাম, মানে বি কে প্লাস ধরলাম তখন হচ্ছে অন্যভাবে হতো।
হ্যাঁ, but হ্যাঁ যদি কোশ্চেন ওটা বলতো yes, then we do this the other way around. Yes, vice versa. আচ্ছা, এখানে কোশ্চেন was the symbol for a capacitor connected to provide the smoothing of the potential difference across the resistor. The capacitors are actually always provided in parallel with the load resistor. So this, you can draw this capacitor right over here. This is the most common answer. Some people can also draw the capacitor over here. This is also possible to achieve. So you can draw this over here as well. Don't draw two. Either of them is okay. I personally like this one because this one makes me understand it better or to explain it better. But holding it over here is also a logically correct option because that's these 2 points are electrically they are the same point. Then it says that on figures 4.2 show the variation of the temperature of the smooth potential across the resistor R. What? We already have a smoothing. So let me have a look at that question. Acha. Oh, Figure 4.2 shows the variation with time t of the smooth potential V across the resistor R. So they are given the smooth potential difference. So these are the smooth graphs. State the interval of time during which the capacitor is being charged from the transformer. So capacitor is charged from T1 to T2. This is the part of the time when the capacitor is charged, and also the load resistor is also run by the supply power. And this is the duration when the capacitor is drained. So every single time the voltage is going up, capacitor is charging up to that voltage, peak voltage of the supply. And as the supply voltage drops down, the capacitor drains to maintain the voltage as best as it can. So the answer to this question answer is T1 to T2. The resistance of the resistance R is doubled. On figure 4.2, sketch the variation with time t of the potential difference of V across the resistance. If you have the double the resistance, then it will take half the time for the, actually half, not half, it will take a longer time for it to be drained, which means the voltage would be kept higher, because you should remember that the equation, the key property for a capacitor circuit was given by the time constant of the circuit, which is given by tau equals to RC. So if you have the same capacitance, but if you have double the resistance, then your time constant will simply become 2 tau. So you will have double the time constant. Having a double time constant means what? If you have a certain capacitor that drains like this, a capacitor that has double the time constant will drain like that. It will drain less over time. So every single time, it would have double the voltage remaining for the same amount of time. Or in other words, I can say that it would take double the amount of time to have the same amount of voltage drained. Or in simpler terms, it will simply drain less. The voltage drop would be much smaller. So if you add a bigger resistance, simply the drop of the voltage would be much less, which means for this entire graph, we would have a much smaller drop. Let me draw that with blue maybe. The peak would pretty much be the same, but simply the drop would be less. So let's say you drop it up over here. Preferably use decreasing, actually I am not drawing it right. I should, if I can't draw a negative exponential shape, because they have pretty much shown straight lines. So I can also, I can also draw straight lines over here. I should try to draw a good straight line. So let's say you are gonna make it a straight line over here. If you choose this point of intersection for your first point, make sure that you hold up your ruler, a horizontal ruler like that, and mark up all of those points over here and over here, so that you do not mess up that location. So let's say I'm going to mark up some points in those places. I don't need that. So let's say one point is over here, the other intersection point over here, because all of these intersection points should have the same level. They cannot be up and down. That would be wrong. And then it would go up, it will charge up, and then it will drain to this new point, and then it will charge up, and then it will drain to this new point, and then it will charge up, and you can just draw
Sir, the voltage change is actually halved, right?
I cannot precisely say whether it's going to be exactly half, because what I can tell you that the amount of duration for which it was draining, here the drain duration was smaller, but here the drain duration is longer. So to be able to find out the exact amount of voltage, that how much voltage is remaining over here compared to the earlier voltage difference, I need actual values present over here and the properties of the R and C values. Then I can do some calculation and can tell you this. I can tell you that it's going to be smaller, but whether it's going to be exactly half, to answer that question, I need actual numbers.
Sir, equation ta to charging time equals to R into C, right?
No. This is a time constant. Time constant means the amount of time within which the initial voltage or charge or initial current of the discharging circuit reduces to 27% of its initial value.
Achha.
E to the power minus 1 করলে যেটা হয়.
Ji, sir.
All right. So that's pretty much it for the Asadul Amin score problems. So we're gonna go for the next problem in the list. Asadul Amin, এই গ্রাফটা কি বুঝছো? কেন এটা আমাদের স্মুথিং হয়েছে? লজিক্যালি বুঝা গেছে কিনা?
জি স্যার এখন ঠিক আছে
মানে
But sir, এমনিতে আমাদের টাইম ডিউরেশন টু চার্জ আপ তো ডিক্রিজড হচ্ছে, হাফ হচ্ছে, isn't it?
what you're proposing, that whether this amount of time is half of this amount of time. That's your
জি
question.
স্যার
I cannot say that because I do not know the exact value of this point. I drew my graph to be somewhere higher. এখন এই হাই পয়েন্টটা আমি এখানেও আঁকতে পারতাম, এখানেও আঁকতে পারতাম. All of these choice of points would be good enough for this question. I do not know exactly where they will intersect unless I know those values.
স্যার টাইম কনস্ট্যান্টটা যে আমরা মানে ডাবল হলো এইটার সঙ্গে আসলে গ্রাফের রিলেশনটা আমি বুঝতে পারিনি মানে is that supposed to affect the time duration for charging or no?
Not charging. Charging will happen when the capacitor, when the supply voltage will reach the value of the capacitor dropping voltage, and then the capacitor voltage will latch onto the supply voltage and it will charge up with the supply voltage. When the supply voltage is going to start dropping from its peak value, that's precisely when the capacitor will start to drain, and it will try to maintain the valve voltage at that level as best as it can till the supply voltage once again reaches its own voltage value. That's precisely what happens right here. So তুমি এই গ্রাফ দুটো বুঝো নাই, that was your question?
জি স্যার ওইটাই
দেখাচ্ছি. কি ব্যাপার হচ্ছে না কেন? আমাকে নেট চলে গেছে?
স্যার ডেসমসও দেখাতে পারেন।
হ্যাঁ স্যার ডেসবসে দেখাতে পারেন
I really can show it in Desmos, but I really don't want to go to Desmos and plot all these graphs right now.
It's a pretty basic one, sir. Just like 1 by x,
Yes.
e to the power 1 by x, something like that.
হ্যাঁ স্যার
Desmos graph. So let's say শুভ দেখো এটা, let's say y equals to initial voltage, let's say 10 or okay, let's go to 10 e to the power, you know,
You can give 1 by x, sir, or minus 1 by x.
আর এরপরে কি দেব? -2 by x.
অথবা 1 minus 1 by ax লিখতে পারেন, তারপর একটা স্লাইডার আসবে স্যার।
e to the power কোথায় যাবে না? e to the
জি
power
স্যার।
fraction হচ্ছে fraction কই?
স্যার ডিভিশন সাইন দিলে ফ্র্যাকশন।
আচ্ছা, so let me give brackets because I want to give brackets. Minus a by let's say
bx
x. এরকম ইকুয়েশন 1 by rc minus 1 by t by rc t by rc না, x by a হবে, সরি,
স্যার।
x by a. আচ্ছা, add slider a, so মনে করো এখানে a এর ভ্যালু হচ্ছে এরকম, ঠিক আছে? So let me zoom in the graph. So এটা হচ্ছে মনে করো আমাদের ক্যাপাসিটরের বেসিক ডিসচার্জ গ্রাফ ফর the value of x is the time. এখানে x হচ্ছে টাইম আর এটা হচ্ছে মনে করো আমাদের tau. That's the basic equation that I equals to I naught e to the power minus t by rc. So if we just make this tau double, let's say can I copy this equation over here? Control C, Control V. So now we have both the graph in the same value, but if I now give this a value here, let me just make this value of a.
Sir, you can just put 2a, like minus x by 2a.
So এই জিনিসটা দেখো, so have a look. Whenever we have the graph with x equals to a, this is the discharge graph, and whenever we have double the time constant, then this is the discharge graph. So here it is discharging much more slowly. So now the question that you are asking, that is it going to be exactly half, I cannot essentially say that. Is it exactly half for all the values?
মানে স্যার গ্রিন গ্রাফটা হচ্ছে যখন রেজিস্ট্যান্স ডাবল করে দিছি তো।
Yes, precisely. So it is discharging less. So ওই জন্য এখানে জিনিসটা হচ্ছে যে এইটা যতটুকু শার্পলি ড্রপ করতেছিল, এটা তার থেকে কম শার্পলি ড্রপ করবে। So that's why it's crossing on the upside. বুঝছো?
মানে স্যার যে টাইমটা হচ্ছে আসলে মানে the time taken has increased, right?
Yes. To drop to the same value of voltage, the time taken has increased. Yes. Or within the same amount of time, the drop is less.
Yeah, but ওটা এক্সাক্ট হাফ না সেটা আমরা মানে গ্রাফের মানে ই টু দি পাওয়ার গ্রাফ থেকে আমরা বলতে পারবো না।
I cannot. Maybe some people can, but I need actual mathematical numbers to be able to calculate this and tell you the answer. All right. So that's that. And then we have some question from Mugdho. It's from May June 14, 42, question number 4b2. Let's have a look at that one. May June 14 is 1442. Should we close this one? 42. Question number 4b2. A helium nucleus contains two protons. In the model of helium nucleus, each proton is considered to be a charge point mass. The separation of these 2 point charges of this point masses is assumed to be this many meters. For the two protons in this model, calculate the electrostatic force. আচ্ছা এটা সহজ, Q1 Coulomb's law দিয়ে বের করা যাবে। The gravitational force এটাও সহজ, প্রোটনের mass আমরা ফর্মুলা শিট থেকে নিয়ে এটা করে ফেলতে পারবো। আচ্ছা, using assumption A suggest Y, there must be some other force between the protons in the nucleus. আচ্ছা, well, the gravitational force is the attractive force that is supposed to bind them together. The electrostatic force is the repulsive force. আচ্ছা এটা তো তোমার প্রবলেম, প্রবলেম শিট 2 তে। Why the additional force must have a very short range? Why this additional force must have a short range? Okay, that's a good question. I need to think. I mean, why can this force have a long range? That's what I'm trying to think about. I'm trying to think about in the other opposite direction. Why it cannot have a long range?
স্যার কোয়েশ্চেন নম্বর কত এটা?
ওই যে মুগ্ধর কোশ্চেনটা দেখো, অলসেটা দেখো।
স্যার চ্যাটে মনে হয় নাই, আপনাকে কি প্রাইভেটলি মেসেজ
No,
করেছে?
no. It is in the chat.
I mean লেটে আসছি স্যার, তাই মনে হয় আমার আসলে।
আচ্ছা, এটা হচ্ছে May June 14, question number 4b2. May June 14, 42. এই যে এখানে দেখতে পারো May June 14, S14, 42, question number 4b2. Muthu, I really don't know the answer of this question. This is something new for me, so I'll have a look at the mark scheme. something new for me. Good. Outside the nucleus, there is a repulsion between the protons. Either attractive force must act only in nucleus, or if not short range, all nuclei would stick together. This is the answer that I was looking for. Acha, makes sense. What it says is that the attraction force that is responsible to overcome this strong electrostatic repulsion force and actually keep the nuclear structure stable, we need that attractive force. But the range of this attractive force has to be very small within the boundary of the nucleus, because if this was not true, then if this force has a really this attractive force had a very large range, then all the other nuclei should be attractive as well. So the nucleus of all the objects should actually merge together. That way, the whole structure of atoms and the molecules and the physical world that we, as we know it, would not exist. So, because the range of this force is too small, it only works within the small range of the radius or diameter of the nucleus, so that the nucleus can hold together because of this attractive force. But if it was bigger than that, or for example, let's say if it was theoretically infinitely ranged as electrostatic force or gravitational force, then all the other nuclei of other molecules or other atoms would also be under this attractive force influence, and they would merge together. So that does not happen. That is something that we not see. So we are not essentially saying that why this is happening. We're essentially saying that an outcome for why this is important. So the masking precisely tells us that outside the nucleus there is repulsion between protons. This is something that we know. This is the statement. And the attractive force must act only in the nucleus. That's the statement. Or if it was not in short range, all nuclei in this case essentially mean the nuclei of all the known atoms that we have, they would tend to stick together. So yeah, it makes sense. I'm interested to see the examiner's report of this question. This should have some really interesting insight.
Sir, first point আমি বুঝিনি outside nucleus এর pointটা.
Within the nucleus, the protons should be attractive because of this attractive force, which is supposed to have a short range. But if you have two protons outside the range of nucleus, which means they are pretty far, they are significantly far apart from each other, more than that distance that they have given over here. Think of any two random protons, not essentially belonging to a single nucleus. If you consider those two protons with each other, just in regular perspective, they would basically repel each other. The reason they would repel each other because of the electrostatic force. Because within a typical or considerable amount of distance between two protons, this attractive force would not be in effect.
So, sir, they're basically considering a normal scenario.
Yes.
Oh, okay, sir, I got it. Thank you, sir.
Sir, force-টা attractive হতে হচ্ছে কেন?
Because the gravitational force would have a much smaller value compared to the repulsive the electrostatic force. So to make sure that the nucleus actually stick together, there had to be a stronger attractive force to overcome that electrostatic repulsion. I want to see this one again. Very few candidates appear to have any appreciation of the situation. There were many references to electrons and neutrons. The fact that the attractive force must act only within the nucleus because outside the protons repel each other was mentioned very rarely. There was a few comments to the effect that all matter would stick together if this force were to be long range. So this question was practically very ill answered as for the mass game. Yeah, makes sense. Yeah, it makes sense to me. But are all of us over here? Are we okay with this? বুঝা গেছে কিনা এই আনসারটা কেন এরকম হচ্ছে? Everyone, any question?
No, sir.
Are you saying something? No. Okay. So we'll pick up the question from Samiha. Yes.
Forces like the strong forces and weak forces যেগুলো আমরা পড়েছিলাম.
Yep. Precisely. The nuclear forces.
So if you mentioned anything about gluons or something, would we still get mark or?
Oh. How would you mention that?
Like gluons are the force carrier that acts only between the protons and neutrons. in very short range.
In very short range, yes. If you write with the additional phrase of within very short range, then you are gonna get that mark. Mentioning the gluon interacting between the protons and neutrons within the nucleus is not gonna be enough. You have to mention precisely that range has to be pretty short for the gluons to be interacted between protons and neutrons. That you have to mention. And there has to be some significant mention that attractive force, for whatever reason you're using the term gluon, perfectly all right, but the mention of that short range have to be inclusive. Bucho?
Yes, sir.
Good. So Samir give us another problem. This is February, March 42, 60 and 6C.
Sir, I asked
Yes.
the question before.
Acha, sorry. My bad. February, March 2017, 42. Acha, we'll pick that up. February, March 2017. (42). Question number. You didn't give the question number. Acha, I'll bring up the whole thing. Don't worry. Close all the tabs. বলো কোনটা?
Question number 8B4.
Question number 8. Let's have a look. State what is meant by magnetic field. A particle of charge +Q and mass m is traveling in a vacuum with speed v. The particle enters at right angle and uniform magnetic field of flux density v as shown in figure 1. The particle leaves the field after following a semicircular path of diameter d. State the duration of the magnetic field. Question why the speed of this particle is not affected by the magnetic field. The duration of the magnetic field. Okay. Conventional current upwards as it enters, force is inward, so field is out of the page. Well, the speed of the particle is not affected by the magnetic field because the magnetic force works perpendicular to the direction of the velocity, which only is responsible for the change of direction. So the diameter of the sensor is going to sound simple. Portable series expression b so that the time tf spent in the field where the particle is independent of the speed in v.
Sorry, I found the expression that in the A1 mark, but I'm not sure if the way I got there will give me like the M1 C1 mark.
So I'm দেখতেছি. Use the expression in b3 to show that the time tf, okay, spent in the field, time in the field tf, okay, by the particle is independent of its speed v. Okay. The time within which, okay, let me just try to solve this on my own. And then I can actually go ahead and do this. This is our question. Copy it. Paste. Okay, so this is the expression that we have, and we want to show that the time spent would be this thing. So here, essentially, the particle is covering a semicircular path. So let's try to subject the t over here. So this is the diameter of the semicircular path. Time spent in the field of the particle. Okay, so if I just write a basic equation, the speed of the particle can be given by the length of the semicircular path, which would be pi d is the 2 pi r. 2 pi r so pi d by 2. This would be pi d by 2. This would be the arc length which it covers through the this thing divided by tf. This would be the expression for our speed of the particle. এটা তো বুঝছো? আচ্ছা আমি আমার মতো করে যাই আগে, তারপর আমি আলাপ করতেছি। এখান থেকে যদি আমি tf কে সাবজেক্ট করি, I'm gonna get pi d divided by 2v. So we're gonna get the d by v ratio. From this equation, if I get the d by v ratio, this is gonna give me
স্যার ফার্স্ট লাইনটা একটু আবার বুঝাবেন?
this one.
জি স্যার।
এটা হচ্ছে এই যে এই তো হচ্ছে আমাদের ম্যাগনেটিক ফিল্ড, এই হচ্ছে আমাদের সেম সার্কুলার প্যাথ, ঠিক আছে? এদিক দিয়ে ঢুকে এদিক দিয়ে বের হয়েছে। সো দিস ইজ এ পারফেক্ট হাফ সার্কেল, সেম সার্কুলার বলে দিচ্ছে এখানে, সেম সার্কুলার, এই যে সেম সার্কুলার বলে দিচ্ছে। তার মানে হচ্ছে এই দ্য ডায়ামিটার অফ দিস প্যাথ ইজ ডি। তাহলে আমার ফুল সার্কামফারেন্স হওয়ার কথা কত? ফুল সার্কামফারেন্স হওয়ার কথা হচ্ছে পাই ডি। সো সেম সার্কুলার প্যাথের এইটুকু লেন্থ হবে কত? পাই ডি বাই 2। এবং এই প্যাথটুকু সে কভার করতেছে হচ্ছে TF টাইম। দিস ইজ দ্য অ্যামাউন্ট অফ টাইম that the particle spend within the magnetic field. So if I divide this distance over time, I get the speed. Speed equals to distance over time. বুঝছো?
স্যার
So ওইখান থেকে আমি TF টাকে সাবজেক্ট করছি টু সি দ্য ইটস রিলেভেন্স। সো TF টাকে সাবজেক্ট করলাম, পাইলাম পাই ডি ডিভাইড বাই 2v। আর এই কোশ্চেন থেকে আমি d বাই v রেশিওটাকে এক্সক্লুসিভ রেখেছি। d বাই v রেশিও গিভস মি 2m বাই v, 2m বাই b কিউব। সো আমি এখান থেকে পাই বাই 2 টাকে আলাদা রেখে দেই, আর d বাই v টাকে এখান থেকে রিপ্লেস করলে 2m by b cube. So mm কাটা চলে যাচ্ছে. So what I'm getting is 2 pi by b cube. 2 pi by b cube. So in this expression, there is no mention of the speed v. So it is independent of the speed. It is only dependent on the sorry, it has to be. It is only dependent on the magnetic field strength, and it is dependent on the particles charge. These are the only two variables which is going to control how long the particle spends within the field, irrespective of its incoming speed. I think that makes sense. Abias, did you understand the calculation the way I went for it?
Yes, sir. Yes, sir. Your method was easier than what I did.
Okay. So
I did like a b is equal to m omega square r, and then did some substitutions and arrived at the same thing. But I'm not sure if I'll get the first mark
can
like
you
the
give me a can you give me a screenshot of your working in the messenger maybe, so that I can have a look? Maybe that can be helpful. I don't get this. 63 people saw this incoming invite, and we have about less than 20 each person in this class. Are these people still doing classes with us, or they just skip the classes because of the gaps? So you did B if you square squared by R, did you give squared by d by 2, R is the d by 2, okay. You still get the mark, and you still get the full marks for it. No big deal. What you did is mathematically correct and logically correct as well. I just did it a different way, but you did it in a different equation, but both the equation perfectly makes sense. You get full marks for it, no big deal.
Okay, sir, I understand. Sir, another one.
Yes.
Is like 9A1. It's just a small one.
Why the core is made of iron?
I wrote, sir, to concentrate magnetic field lines, but the mark scheme said increase flux linkage or reduce flux loss.
These are actually what you wrote is actually the first part of an explanation, and what the mark scheme provided was the last part of an explanation. It actually considers the magnetic field lines to achieve what? The mark scheme gave you the endpoint result or the end outcome of using the magnetic software core. That, yeah, considering magnetic field lines is basically the purpose for which we use the software and core. But how does that help? It makes sure that more field lines cut across the secondary coil, or in other words, it considers the magnetic flux, or it reduces the loss of magnetic flux out of the core. So they wrote the endpoint result, you wrote the first point result. You are not incorrect, but I would recommend that you learn what the mark scheme provided.
Okay, sir. And my last question is from 10B3.
10B3.
10B2, sir.
Okay. Light is a beam of continuous
Actually, 10B2.
spectrum that lies within the visual region. The photons of light have energies ranging from 1.6 electron volt to 2.6 electron volt. The beam passes through some hydrogen gas. Then passes through a diffraction grating and absorption spectrum is observed. All of the light is absorbed by the hydrogen. It's re-emitted. Somehow the dark lines are still observed in the absorption spectrum. Oh, this is pretty simple. I'll tell you why this is. Is your question was B1 or B2?
B2, sir, B2.
Achha. Some of the energy levels, some electron, hydrogen. The darkness and should be energy levels. Achha. In this case, the arrows will be upwards because the absorption spectrum means the electrons absorb those energies and they jump to the higher level. And eventually, when they emitted those lights, they emitted in random directions. So they are not essentially going in the same direction as the incoming light direction. That's why the detector placed on the other end of the source light wouldn't be able to detect all those. So because this is an absorption spectrum, the arrows would be upwards. For an emission spectra, the arrows are downwards. Electrons, as the electrons come down from high energy level to low energy level, they emit the electrons. That's for the emission spectra. Most common example, like flame test and everything. But for absorption spectra, the electrons should go up as they absorb that specific energy and they would jump upwards. So these arrows should be upward direction. So here we have
emission spectrum হলে কি নিচের দিকে হতো arrow গুলো?
Yes. Emission spectrum means as the electrons are de-energized, they emit up those photons equivalent to their energy range. So 1.6 to 2.6. So you have to find out the gaps relevant for this amount of change. Darkness.
So the thing is, I find the maximum is from 3.4, 1.51, and 3.4 to 0.454. The thing is, you don't exactly get the values.
No, you are not supposed to get the exact values. Have a look. The photons have light energies ranging from this to this, which means you should expect that all the values, inclusive the boundary values, you have all the photon energy values of these values available. So whatever the value of the photon energy that perfectly matches for the gap boundaries, those would be missing. It's not precisely those values. It's then inclusive values. So let me pick up the whole question. Come to see. So if we go for the calculation for over here, the energy gap over here is how much? This is 0.31. This is, how much is this? Actually, I don't have to do all this calculation, to be honest. I'll make the calculation easier because I can already see that these are the ranges from 2.6 to 1.6. So I will definitely not get any jumps over this range because this is too big. You can see that it's about within 10.2 is the difference over here. So I'm gonna start dropping from here, and the jump can be only here from upwards. So from here to here, this is how much? Do the subtraction, please. Have a look. 3.4 minus 1.51. 3.4 minus 1.51. 2.2. This is possible. And from here to here, this is how much? 2.55. This is also possible. And then from here to the top, 3.40 minus 0.54, 2.86. So this is not going to happen. So I'm going to have two arrows from here to here and one arrow from here to here. But can we get another arrow from here to the any of the other parts? 1.51 to 1.85, this will not work because the starting value is only 1.60. So nothing would be happening from here to here, because if you do the differences of these values, I mean 1.51 to 0.85 or 1.51 to 0.54, you're gonna get values that is smaller than this electron volt value. So only these two arrows are relevant. I mean, these are the only two values which fall within this range, 2.25 and 2.55. These are the only two values which fall within this range that is possible for the electron gaps, energy level gaps.
Got it, sir. G, sir. 3.4 to 1.51 is 1.89, the difference.
Which one?
The difference between 3.4 and 1.51, I think it's 1.89, sir.
Yeah, 1.89 falls within the boundary.
Yes, sir. Yes, sir.
Achha, I wrote this wrong. My bad. Achha, calculation error. But yeah, it makes sense. R?
Yes, sir. Thank you.
Okay. We get the question from Samiha. Samiha gave us a question from February, March 42, 16, 6C. So let's go for it. February, March 16, 42. Might as well open that, isn't it? Why not? 16, 6, 6C. Okay, here's the question. A parallel beam of ultrasound is incident normally on the surface of a layer of thickness 1.1 centimeter. Fact. For the ultrasound, I1 is the intensity just after entering the surface of the fat layer. I2 is the intensity incident on the fat muscle boundary. I3 is the intensity back on the fat muscle boundary. I4 is the intensity back at the surface of the fat layer. Some data for the fat are given: specific impedance, density. Why did they give density? For whatever reason, they gave density. Calculate the time interval between a short pulse of ultrasound initially entering the layer of fat and then returning back to the surface of the fat layer. Achha. So from here, you have to find out the speed of the sound using this information, and then using this part, you have to do V equals to 2D. Find the time back to the surface of the fat layer. Achha, okay, fine. You can calculate this, no problem. Calculate the ratio of I2 by I1. I2 by I1 would be given by the absorption coefficient, so that's possible. And then it says the intensity I4 is 0.33% of I1, determine the ratio of I3 by I2. Nice question. Okay, I'll solve this. Just give me a moment. Okay, I was in the recording. So determine the ratio of I3 by I2. I'll need the whole picture. Yeah, this should help. No, this one. No, I have to minimize this one first. No. Keep it there, and then Sana, তুমি আসো?
Yes, sir.
All right. So bear with me. I'm going to press it side so that you can see the whole question. Beautiful. So এখানে আমাদের এই কোশ্চেনটার আনসার কত আসছে? Give me in bit longer decimal places if you can. এটা কত আসছে?
Sir, আমি 0.59 আসে।
0.59 আচ্ছা ঠিক আছে, সমস্যা নেই, থাকুক। The intensity I4 is 0.33% of intensity I1 determine the ratio of I3 by I2. আচ্ছা, আমি এই জিনিসটার প্রসিডিউরটা একটু আগে এক্সপ্লেন করি। Let me explain how this whole thing is happening, and then we can go back. We did a question like this where we had to go through. So what is going to happen is going to go through this fat layer, undergo absorption, then it's going to reflect of this boundary. So because of the reflection, there will be some reflection coefficient involved, and then it's going to come back to the same level. So there's going to be three different stages of reduction. First, we're going to have one reduction. We're going to have one reduction for the transmission, one reduction for the reflection, and then another equal amount of reduction, equal fraction of reduction for the transmission back. So the ratio of I2 by I1 and the ratio of I3 by I4 by I3 should be exactly same. So if I write it in this format, so the ratio of I2 by I1 was 0.59. So what I need to understand that I4 by I1 should be equals to 0.59 into I3 by I2, because you have to understand that the I3 is supposed to be the stronger intensity, which is falling onto the boundary, and I2 is supposed to be the weaker intensity, which is the reflected boundary. So that's why the small by large, because that's how the reflection coefficient works. The smaller fraction is always on the numerator side, into 0.59. এই হিসাবটা বুঝতেছো কিনা আগে দেখো।
স্যার বুঝি নাই।
বুঝাচ্ছি। I4 by I1 means the incoming intensity ratioed by the total output intensity. So whenever it will travel through, first this incoming intensity travels to the fat layer once. So this is the reduction due to the transmission, which is the ratio of I2 by I1, which we get by I equals to I naught e to the power minus mu x. That ratio. That's a transmission reduction. বুঝছো? এটা তুমি
I2 by I1 এর ব্যাপারটা আরেকটু।
হ্যাঁ, দাঁড়া এক মিনিট, সামিহা বুঝে নাও, তারপর শুরুকে একটু পরে কোশ্চেন করো। সামিহা কি বলছিলা?
স্যার মাল্টিপ্লাই কেন করলেন ওটা বুঝলাম না।
মাল্টিপ্লাই করলাম কারণ হচ্ছে because this incoming value would actually become reduced by all of these factors, and the total final outcome that you're gonna get, is going to be the product of all of these things. For example, let's think of one thing. Let's say you have a certain value, let's say that a number that is, let's say 1000. If you reduce it, if it becomes, let's say 15% first, then it becomes, let's say 20%, then it once again becomes, let's say 30%. You can practically multiply all of these things to get the total percentage decrease. বুঝছো কি বলছি?
জি স্যার, আলাদা আলাদা করলে একই হবে।
হ্যাঁ, ওই জন্য আমি এখানে সবগুলো রিডাকশন রেশিওকে ইন সিকোয়েন্স তোমাদের জন্য আলাদা করে দেখালাম। সো দিস ইজ দ্য ফার্স্ট transmission reduction as it was going through the boundary. This is the reflection reduction which we are trying to calculate out. This is the part that we have asked to calculate, and then it's going to come back through the boundary, so we're going to have another reduction of the same fraction. And
সেম কেন হচ্ছে ওই পার্টটা বুঝলাম না।
Because it is the same amount of medium. I mean, e to the power minus mu x. Mu is the same, x is also the same 1 centimeter. So this part, এই পার্টটুকুর ভ্যালু হচ্ছে বেসিক্যালি 0.59, তাই না? তো যাওয়ার সময় 0.59 যতটুকু হবে, আসার সময় ফ্র্যাকশনটা সেম থাকবে না? এটা বুঝো নাই?
সেম হচ্ছে স্যার।
কনফিউজ লাগতেছে।
আমি বলতেছি, try to think about it. The fraction of reduction you're going to get as the incoming signal experiences going through a 1.1 centimeter fat from left to right, shouldn't the same fraction of reduction work as another signal comes from right to left to the same thickness of material? I mean, if you do the ratio of I equals to I to the power minus mu x, the value of this e to the power minus mu x, a muta value হচ্ছে এটা, x হচ্ছে 1.1 centimeter. So are you going to get a different value for this number? This ratio is basically what? I divided by I naught, তাই না? Equals to e to the power minus mu x. এই I divided by I naught-টাকে এখানে আমরা কি দিয়ে লিখছি? I2 by I1 দিয়ে লিখছি। I2 হচ্ছে আমাদের transmitted fraction, আর I1 হচ্ছে আমাদের incoming fraction. So basically that one is having a reduction factor of e to the power minus mu x. ঠিক কিনা?
স্যার সেকেন্ডটা যেটা করছি 0.59 ওটা কি হচ্ছে রিটার্ন করছে এটা ফ্যাটের মধ্যে দিয়ে রিফ্লেক্টেড পার্টটা ওইটার জন্য।
Precisely. So as I3 is coming from this boundary going to the left and reaching up to the first boundary of the fat, that I3 would be reduced by another factor of 0.59 as it will become I4 when it reaches over here.
আর I3 বাই I2 টা কোনটা স্যার?
I3 by I2 টা হচ্ছে যে এখান থেকে আমাদের একটা সার্টেন ফ্র্যাকশন অফ এখানে পড়লাম। আমি তোমাকে জিনিসটা নাম্বার দিয়ে দেখাই। ফর এক্সাম্পল লেট মি ইউজ এ ডিফারেন্ট কালার। লেটস সে মনে করো দিস ইজ 0.59 তো 59%। সো মনে করো এখান থেকে আমাদের 100% এর একটা সিগন্যাল ঢুকছে। As it travels over here, currently এই সিগন্যালের 59% already সেই রিডাকশন হয়ে গেছে। So now we have something remaining. Let's say this was 100. This is 100 minus 51 কত হয়?
So 41.
41. So now let's say this is a value of 41. Now this entire 41 value would not be reflected because this is a surface where we're going to have some reflection. Reflection এর জন্য আমাদের একটা ফর্মুলা ছিল I reflection divided by I intensity incident is given by Z1 minus Z2 whole square divided by Z1 plus Z2 whole square. Remember this thing?
জি স্যার।
ঠিক আছে, এখন এই ইকুয়েশনটা আমরা ইউজ করতে পারতেছি না বিকজ আমাদের মাসেলের Z1 এর ভ্যালু দেওয়া নাই, আমাদের শুধু ফ্যাটের স্পেসিফিক ইম্পিডেন্স দেওয়া আছে। যদি এই ভ্যালুটা দেওয়া থাকতো তাহলে আমরা সরাসরি এই জিনিসটা এই রেশিও দিয়ে ক্যালকুলেট করে ফেলতে পারতাম। আমাদের এই মাসেলের স্পেসিফিক অ্যাকুস্টিক ইম্পিডেন্স কোশ্চেনে দেওয়া নাই। We don't have that value. So we cannot use this equation. That's the limitation that we have to begin with. এই পার্টটুকু বুঝো। But essentially this would fit over here and a smaller fraction of this 41 would be bouncing back. Let's say that smaller fraction is, let's say now it becomes 23. I'm assuming 23.
এই ডিক্রিজ পার্টটুকু কি কিছুটা ট্রান্সমিট হচ্ছে আর কিছুটা রিফ্লেক্টেড?
Precisely. So 41 এ আমি যদি 23 যদি রিফ্লেক্ট হয়, if you do the subtraction এখানে কত থাকবে? 18 18 is it 18? 43 minus 21 করলে কত হয়?
জি স্যার 18.
This would mean that if I'm just assuming this number, don't take my word for granted, but I'm just assuming this number. So if 41 intensity falls over here and 23 reflects, it does mean that 18 would be going through and 23 will be reflected back. And this 23, as it will travel all the way up to this point, let me use red once again, as it will travel all the way up to this point, this will also be used by a fraction of 0.59. So if you multiply 0.23 into 0.59, 23 into 0.59 কত হয়?
So 13.6.
So 13.6 amount loss হয়ে যাবে। So তাহলে আলটিমেটলি আমাদের I4 এখানে রিচ করবে কতটুকু? না সরি আমি কি ভুল করতেছি? I'm doing the subtraction. Am I supposed to do the subtraction? I'm ভুল করতেছি অ্যাকচুয়ালি। এখানে 41 হওয়ার কথা না। Sorry, Samia, I'm extremely sorry. I was a bit getting forward. এটা received part হচ্ছে 59. This is the part that is actually transmitted through. We are not supposed to subtract this. কতটুকু অ্যাবজর্পশন হয়েছে সেটা বাই করতে হলে আমাদের সাবট্রাক্ট করা লাগবে, বুঝছো? মানে I equals to I naught, আচ্ছা আমি আবার লিখি I equals to I naught e to the power minus mu x. This is the transmitted
59% ট্রান্সমিট হয়েছে।
Exactly. আমি ভুলে সাবট্রাক্ট করে ফেলছিলাম, my bad.
যেটা অ্যাবজর্বটা আমরা বের করে ফেলছিলাম।
হ্যাঁ, ভুলে অ্যাবজর্বটা লিখে ফেলছিলাম, my bad. So 59 এখানে পড়তেছে, তো এখান থেকে মনে করো যদি 18 যদি
18 টার পুরো ট্রান্সমিট হবে না, কিছুটা তো আবার মাসল থেকে রিফ্লেক্ট হবে।
হ্যাঁ এক্স্যাক্টলি। এখন মনে করো যদি 18 যদি আমাদের ট্রান্সমিট হয় তাহলে আমাদের রিফ্লেক্ট হওয়ার কথা কত? I'm gonna change this number. এটা এখন সাবট্রাক্ট করে বের করো। 59 minus 18 করলে কত হয়?
So 41.
41। তো এখানে মনে করো আমাদের 59 minus 18 করলে 41 হয় না?
জি স্যার।
আচ্ছা, let me use a different number. Not too confused. Let's say this is 20. তাহলে কত হয়? 39. 39 is a good number. So এখন আমাদের 20 fraction 20 ইন্টেন্সিটি যদি ট্রান্সমিট হয় তাহলে এখানে আমাদের এই পয়েন্টে রিফ্লেক্ট হবে হচ্ছে 39 ইন্টেন্সিটি। এই 39 ইন্টেন্সিটিরও 59% আলটিমেটলি এখানে রিচ করবে। সো 39 59% করলে কত হয়? 39 into 59 is 0.59 করে দেখো কত আসে? 39 into 0.59 23। তার মানে আলটিমেটলি আমার এই সারফেসে এসে 23 রিসিভ হবে। এই হচ্ছে টোটাল হিস্ট্রি। তার মানে আমার ট্রান্সমিশন রিলেটেড মানে থিকনেস রিলেটেড যে এই ফ্র্যাকশন রিলেটেড রিডাকশনটা হচ্ছে দুইবার, যাওয়ার সময় একবার, ব্যাক করার সময় একবার। আর রিফ্লেকশন রিলেভেন্ট যে রিডাকশনটা সেটা হচ্ছে একবার। এটা হচ্ছে সেই রিফ্লেকশন রিলেভেন্ট অ্যাবজর্পশনের যে রেশিওটা, সেটাকে আমি এই ফরম্যাটে লিখছি I3 by I2।
এটা রিফ্লেক্ট আর ট্রান্সমিট করে যেটা হয়ে থাকে আর কি, বের হয়ে আসতেছে।
এক্স্যাক্টলি। আর এটা হচ্ছে ফার্স্ট বারের জন্য থিকনেস ফ্র্যাকশন, সেটা হচ্ছে সেকেন্ড বারের জন্য থিকনেস ফ্র্যাকশন। অল টুগেদার এটা হচ্ছে আমার টোটাল রেশিও, যে ফাইনালি কতটুকু পাবো। এখন দেখো এই কোশ্চেনে বুঝা যাচ্ছে কিনা।
জি স্যার, এখন বুঝছি।
বিউটিফুল। সো এখন তুমি I4 by I1 এর ভ্যালু বসাও, এখানে আসবে হচ্ছে 33/100, আর এখান থেকে I3 by I2 ক্যালকুলেট করে দেখো তো কত আসছে, আনসার ম্যাচ করে কিনা দেখো।
Sir, 33/100 নাকি 0.33/100?
Oh, sorry. হ্যাঁ 0.33/100, my bad, ভুল দেখতেছি আমি।
Sir, I didn't get one thing.
বলো।
With 39 টা বুঝি নাই স্যার।
39টা হচ্ছে যে দিস ইজ এই নাম্বারটা কোথা থেকে আসলো?
জি স্যার।
I assumed, just to make sense with numbers, that let's say of the 59 value of intensity that falls onto the fat muscle boundary, 20 intensity penetrates through. I assumed this number out of nowhere. If 20
Okay, sir.
amount of intensity goes through, then the remaining intensity should be reflected. So I just did the subtraction and got this number.
Okay, sir.
Shower thoughts, brr. Right, what does that mean?
Sir, it's the new meme language, sir. I don't get it either.
Should I Google this?
Sir.
হ্যাঁ শুভ্র বলো। হ্যাঁ
স্যার I2 by I1 এর ব্যাপারটা আরেকবার একটু বুঝান তো, কিভাবে 0.59 আসছেন আপনি? এই জায়গাটা আমি আসলে ভুলেই গেছি কিভাবে কি করে।
আমাদের ট্রান্সমিশনের ইকুয়েশনটা হচ্ছে I equals to I naught e to the power minus mu. This is the primary equation that we have learned through our theory discussions. So I is the transmitted intensity that is available after a thickness transmission of x thickness, where mu is the absorption coefficient of that medium, which means if you have a medium of x thickness, you send in a initial intensity of I naught into the medium. It travels to the medium of thickness x, and at the end of the medium, the available intensity would be I. So that's the expression. So if I take this thing on the lower side, I can write I by I naught equals to e to the power minus mu x. So the numerator is the available intensity after the traveling, and the denominator is the starting intensity. So এই কোশ্চেনে এখানে তো আমি সব হিজিবিজি করে ফেলছি, মেইন কোশ্চেনটাই দেখো। এই কোশ্চেনে তোমার ফরওয়ার্ড গোয়িং ট্রান্সমিশনের স্টার্টিং ইন্টেন্সিটি ছিল I1, এবং after passing through the medium, the heating intensity was I2. The reflected intensity was I3. These two are not equal because whenever reflection happens, some amount would be transmitted through. That's why these two cannot be equal. So this is the available intensity after passing through the fat layer of 1.1 centimeter. So I2 is the transmitted intensity, I1 is the initial intensity. So I2 divided by I1 equals to e to the power minus mu into 1.1 centimeter. বুঝছো?
স্যার আরেকবার বলুন I2 ওই পার্টটা কি বললেন?
This is what I meant. I'm going to write, no problem. What I say is that I2 divided by I1 equals to e to the power minus mu into 1.1 centimeter.
আচ্ছা স্যার মিউটা কি ছিল জানি, মানে কনস্ট্যান্টটা কত
দেখো।
আচ্ছা, আর স্যার আপনি সিতে হচ্ছে দুইবার 0.59 দিয়ে মাল্টিপ্লাই করছেন, বিকজ একবার মানে ভেতর দিয়ে আসার পরে আবার হচ্ছে মানে রিফ্লেক্ট করে ব্যাক করছে ওইটার জন্য।
রাইট, এক্স্যাক্টলি।
0.59 I3 by I2 হচ্ছে মানে জাস্ট অ্যাবজর্ব কতখানি হয়েছে মাসলে।
এক্স্যাক্টলি।
ঠিক আছে, বুঝতে পারছি।
অলরাইট, আর কোনটা?
স্যার আমার এরকম সিমিলার একটা প্রবলেম ছিল ওয়েন 18 এ।
189
4.2
ঠিক আছে
variant 4.2
দেখাবো সমস্যা নাই although the class time is actually really far over so for any of you who want to leave you can leave but I'm gonna cover this problem and eventually we'll call it a day for today কোনটাতে বলা একবার ON 14
So ON 18 variant 4.2
ON 18 variant 42 কত নম্বর
স্যার একদম লাস্টে যেতে থাকে নিচে স্যার এইটাতে
got it আচ্ছা the RMS voltage of a voltage transmission multiple supplies and frequency supply frequency and it's a function of the okay a parallel beam of extra intensity I naught is instead normal under some soft tissue and bone as 10.1 implicit I naught the bone is 0.40 centimeter thick and the total thickness of the bone and the soft tissue is 1.8 centimeter. Therefore, linear attenuation absorption coefficient mu of bone and soft tissue given equation. Therefore, the ratio transmission density by instant transfer terms of decibel. All right. The ray passes through here. So we are only in this case asked to calculate the absorption coefficient. They have not given us the reflection boundary situation, which is bad. There would be some reduction for the reflection as well, but they haven't given us any of this information. So in this case, we have to skip that part. Although that's not realistic. বুঝাচ্ছি আমি কি বলতেছি আমি কোশ্চেনটা কপি করে নেই
স্যার এখানে কি বোন থেকে রিফ্লেকশনের কথা বলছেন
বোন থেকে রিফ্লেকশন হবে মানে when the আমি এখানে নিয়ে নিই তারপর বলতেছি আমি just a second so what I was about to say is that intensity income intensity enters at I naught whenever it will travel from the soft tissue into the bone boundary there will be a reflection relevant reduction and then it is gonna go so in this process of medium change a portion of the incoming intensity will be reflected back and the remaining intensity should pass through the bone and the same thing would once again happen when the beam would essentially pass from bone into the soft tissue boundary but in this question they haven't given us those specific acoustic impedance values
স্যার রিফ্লেক্টর পার্টটাকে কনসিডার করব না
that's what I'm trying to guess because they haven't given us this information so in this case because they haven't given us this information because if we had to consider that the whole math would become really frantically large I can show you but let me just do this one first and then I might actually show you if you're interested so here the idea would be pretty simple that this is my ultimate available intensity and this is my incoming intensity I'm gonna having two different absorption because of the two layers so e to the power minus mu into fat should I write fat let me just write fat is a smaller word let's assume that's the soft tissue into e to the power minus mu of bone so that's basically you are trying to calculate so here if I do the ratio I by I naught equals to e to the power minus mu এখানে ফ্যাটের মিউ হচ্ছে 0.92 into ফ্যাটের থিকনেস হচ্ছে 1.4 into to the power minus বোনের হচ্ছে 2.9, বোনের থিকনেস হচ্ছে 0.4। এখান থেকে আমাদের একটা ভ্যালু আসবে। দেখো তো এটা কত আসে?
0.0865. 0.0865.
Sir, for X-rays, is reflection a thing of consideration?
আচ্ছা, আর এটাকে আমার দেখেন ডেসিবেলে কনভার্ট করতে হবে। ডেসিবেলে কনভার্ট করতে হলে do we have to log this? I don't know how to convert this into decibel.
So এটা আমি বুঝি নাই।
আচ্ছা দাঁড়াও মার্সিয়ান দেখি, because they were asking the answer in decibel, right? They were asking the answer in decibel, so how to convert that into decibel? I'm not sure about that. I'll have to look for it. W18 10C দেখতেছি, দাঁড়াও বুঝাবো, don't worry. Right, they just took log on both sides and then immediately 10 multiplied by 10. So this is what they did. So I'm gonna write I divided by I naught. If I take log on both sides, what you're gonna get, log করলে কত হয় নাম্বারটাকে? Log
So minus 1.06.
minus 1.0629 বেল। তো এটাকে ডেসিবেল করতে হলে আমার মাইনাস 10 দিয়ে মাল্টিপ্লাই করতে হবে, 10.629 ডেসিবেল। আর 2SF এ যদি রাখো তাহলে হচ্ছে মাইনাস 11 বেল, আর যদি 3SF এ রাখো তাহলে হচ্ছে
ডেসিবেলে চেঞ্জ করতে গেলে কি লক করতে হবে?
হ্যাঁ হ্যাঁ, minus 10.6 decibel যদি 3SF এ রাখো। That's pretty much the answer, I believe. হ্যাঁ, so log in নেওয়ার জন্য they had decibel নেওয়ার জন্য they had to just take it into log on both sides. That's basically what they did. If you wonder where does this actually come from, if I try to add some additional reference to this, the way we did the transmission process was that we had a communication channel. Remember this, we had a communication channel, we had a incoming transmission. This was the sending transmission, this was the receive transmission. The idea was that the attenuation was calculated in a log scale. We could have calculated the attenuation only in IR by IS value. We could have calculated this value. This would give us a number which would be somewhat of like this small, I mean very small but long digits after the dot point, and this would give us something like this. To avoid that long this fraction long decimal small numbers, what we did is that we simply applied log over here. By applying log over here, we could make the whole long, I mean a very long decimal number into a shorter version. So because we took a log over here, I mean this is the attenuation that would have been, but if we do the log of this one, we'll definitely get some minus number in bell, and just to make it into decibel, we would get this one 10 multiplied by bell. To avoid this minus sign, what we did is that we reverse this thing. We put the send signal implicit on the numerator side and receive signal at the bottom, so that we could get rid of the minus. But because we are saying attenuation, this would essentially mean that the signal is getting low power, so it is losing power. That's basically it. বুঝছো কি?
Yes, sir.
So এখানে যে আমরা মাইনাসটা পাচ্ছি, this minus is basically meaning that the signal is becoming decreased. In our communication channel, we implied that minus sign by using the word attenuation. Attenuation essentially means the loss of signal power over a communication channel. So I think that makes sense.
Sir,
Yes,
are in any case with X-rays, are they ever reflected from like body matter?
they do.
Is it like wouldn't it be a very small amount, sir?
Even though if it is very small amount, this can actually significantly make our observation misleading, because the detections are made. The detectors for the X-ray beams on the receiving side have to be really precise if you want to get a precise data output of your X-ray propagation. We can get rid of that reflection related problem by using collimators.
The things that make beams parallel, sir.
Yeah, precisely. So what I was saying is something like this. We have an image of what you just asked. Here you can see that there are some random reflections of the X-ray beams. These reflections are happening because of the heavy metal ions that we have in our bloods, or some other particles which are capable of physically reflecting the X-ray beam. So we have a lot of transient reflection beams which are not being parallel. We are absorbing all of these parts using a collimator, so that only the parallel beams are going through, so that we can actually have a good contrast picture that here we have muscle, and here we have muscle, and here we have bone. So bones are no beam is passing to the muscle part, bone part, and beams are actually passing to the flesh part. You can actually see that. Buchike will say.
Ji, sir.
Beautiful. All right, let's call it a day. These are some good questions. I learned new stuffs, and yeah, it helped. I'd actually include these additional questions in my decision for the next year's to batch in the regular lecture class, because these are stuff that the students should know how to handle. Good question picks. Thank you, kids. For those who shared questions, for those who did not share questions, I assume that you didn't do your homework. I have reasons to assume that. So I'm holding you responsible. I'll call out names next class. Thank you very much. Good night.